Okay, sorry about that. Should be able to hear me on the stream now. Thank you so much for saying that. We were just chatting about how thermodynamics is a disappointment. So you didn't miss anything. There's some frustration here with thermodynamics, and I was doing my best to relate. So in my undergraduate, so you guys I think know that I had my undergraduate was actually science, but it was closely paired with engineering because like the whole school's engineering. So I ended up taking thermodynamics, but we had a thermodynamics of the Earth systems, which is like thermodynamics of clouds and how to determine vapor pressure and those sorts of dynamics, which I thought was pretty neat. I had a similar experience in that there was not a very clear book to lecture relationship there, but it turned out he was good at teaching. It was interesting stuff. So I lucked out, I guess. And I wish we had something like that here, but all I can say is sorry and good luck. I think I have a textbook that does deal with some thermodynamics of cloud systems. If you guys are ever interested, I could show you that. But anyhow, so today I wanted to kind of wrap up disinfection. We kind of did a half lecture on it for the first lecture, and then last time we did kind of a full session. And so this is, I guess, kind of our third set of slides on disinfection, I think. So I want to talk about ultraviolet light as a disinfectant. And if we get time, I'll show you a few slides on kind of a caveat to ultraviolet disinfection, which is the potential for bacteria to repair themselves after exposure. Now, bacteria could repair themselves after chlorination or other disinfectants. There are different processes, but ultraviolet light is an interesting one because many cells, not just bacteria, have some mechanisms to cope with UV light because it's kind of a natural source of destruction. So we might get to that a little bit. I wanted to talk a little bit about how we consider the UV light as, how can we understand the disinfection rate constant, so to speak, right? We talked about for a chlorine system here, HOCl, for example, if we take that HOCl, we can look at specifically what is that disinfectant's, that chemical's capability of killing a specific organism and look at the rate that way. So with that, back to the slides here. With that, the UV light spectrum is obviously a subcomponent of the EVEG spectrum. And if we take a look at UV light, it really is ranging between realistically 200 to 400. Now, technically, we call 100 to 200 UV as well, but you really need a vacuum in order to be able to transmit any photons of that wavelength because it's all going to be absorbed by the oxygen and other stuff in a gas atmosphere. So realistically, that's why it's called vacuum UV. So realistically, in what we might be able to use in a lab without special vacuum equipment would be 200 to 400. And even that, mostly that's 250 plus. You are getting more and more absorption by oxygen if you're operating kind of in the low 200s range. So visible light is 400 to about 800. And so if you consider ultraviolet, really what that's talking about is we get to violets, which are around 400, and then we go further. And ultra meaning above. Kind of what we're talking about is above in terms of energy. So remember that a wavelength is really talking about the distance between two peaks. So there's some distance here, that's our wavelength, right? Call that lambda. And that wavelength, if you shrink it, the shorter wavelength, that means more waves are hitting your target per time. So if you compare that to a wave that looks like that, if I could draw a good wave, if they're traveling at the same speed, one of them is going to be impacting with a lot more waves right? And I think that what that translates to is a more energetic photon. That photon itself has more energy. So not that there's more photons, but each photon that hits has that extra energy. And so when we talk about a longer wavelength, that's lower energy. So we could say this way is lower energy. Of course, the other way is higher energy. And we could go from vacuum UV to the X-rays, and then on eventually to gamma rays, right? So that kind of encompasses all of those different types of photons. We go from infrared, we could go up to microwaves, radio waves, all of that. So in terms of what we can use for disinfection, we may consider, and well, I'll just show you the solar spectrum. Might pull that up. I need to add it to these slides. I don't have it with me here. But the solar spectrum looks something like you just start having a tiny bit of light coming in, and then it does something like that. And so our visible range here, most of the solar spectrum that we receive at their surface is visible. The atmosphere is absorbing pretty much all of the UVC, most of the UVB, and then some of the UVA, because really the sun is probably emitting, I drew it like that. What it's probably emitting is like that, right? All sorts of chemistry, all sorts of radiation occurring and emitting from the sun. Our Earth's magnetic field deters a lot of the radiation and particles, and then our upper atmosphere absorbs a lot of the ultraviolet rays that could also be a problem. So effectively, what the Earth receives is UV radiation in that range. That's the kind of stuff that UVA will trigger your skin cells to produce more antioxidants, which are also skin pigments. So you want these antioxidants to combat photoexcitations that are going to create reactive oxygen species. So these reactive oxygen things are going to be destroying cell components, going to be causing skin burn, potentially leading to cancer, all of that stuff. You don't really want that. So your body has built-in sensitivity to UVA range light or thereabouts to say, oh, okay, well, if we're exposed to this stuff, let's create more pigments, right? And so you can obviously see then populations of humans that have historically lived in different areas of the world are going to have more or less pigment, kind of based on the need. So the UVB range is really primarily what causes the burns. And of course, this is all a spectrum, right? So that there's, even if you have a specific wavelength that causes some specific reaction, it's not like the 315 nanometers wavelength does it, but the 316 does not, right? It's just, there's probability there in excitation energies and activation energies, all of that. So while 400 is going to be a lot different than 300, once you get into the fine minutia there's, it's not an exact cutoff here. So mostly what you're looking at is skin burn stuff and skin tanning stuff. So that's a bit of a relation there. Really, those are there to, protect ourselves from skin damage. Now, the range we use for what we would call germicidal wavelengths would be in the UVC range. Specifically, we have mercury lamps that emit strongly at 254. We'll look at some spectra like that. Though that happens to be a pretty good one for germicidal damage. It literally damages DNA, and I'll explain that in a couple minutes. And so that's been historically one that we've used quite a lot of. We'll talk as well about some newer technologies with LEDs that can emit in the UV range, and specifically in the UVC range. Of course, these are pretty hazardous to us as humans. We don't want to expose ourselves to UVC light because we don't want our DNA damaged. Even if we have a little bit of protection, a little bit of absorption from pigments, it's it's really not going to be enough to protect ourselves fully. So if you've ever worked in a lab, you may have seen these UVC lights in a microbial bench, and when you have the glass pane shut, you might even have it on, and you might be thinking to yourself, well, shoot, I don't want that UVC light, because this is a mercury lamp here, shining UVC light, low pressure mercury, so we've got that 254 emission. So you might be thinking to yourself, well, dang, I don't want that. I'm going to avoid this lab at all costs while that's on. But if you were to measure, which I've done, you can take a radiometer, and it turns out the glass absorbs all of that light. So fortunately, in the UVC range, you actually have to have very carefully designed glass materials to transmit the light, because it's most glasses are silicon oxides of some sort, and that those bonds absorb UVC very strongly. So you can take a radiometer and you can put it inside there, shut it, and turn it on. You'll sense it. You'll have some amount of light. You just turn it off, pull it out on the outside, put it right up to the glass, facing the light. No photons received because of that. So that's real nice. It also means these lamps are specialized quartz materials to have very high transmittance of the UV light. That becomes really important in water treatment, because we are really concerned that if we're producing this light, we need to get it to the water, and we don't want the surface of our lamp to get all junked up by all these reactions that are probably occurring, and just whatever junk is in the water. We don't want it to get gunked up over time and then try to clean the lamp and then break it, and then we have a little bit of mercury vapor escaping, right? None of that's good. So we actually use a secondary quartz sleeve. We'll talk about that now, to have that secondary sleeve around it to protect it from the water, so you can then wash the quartz sleeve, which also is fragile and but it's a little thicker, it's a little more robust, so it's something a little better. So there's been some innovations here. There are some plastics that can transmit most of the light. So I saw an advertisement. I think it was sort of a technical talk advertisement sort of a thing. I think it was a video, might have been in person. But they essentially made this plastic tube. Instead of using a quartz, they were using plastic and then arranging their lights outside of the water to shine through that tube. And they were saying that, well, that tube's easier to clean. You do have a little less transmittance of the light, but it turns out to be cost effective. So that was one strategy, to have these lamps outside of that altogether. May make some sense sometimes. Normally what a UV dosing chamber is going to look like is this one on top, where you have this system that's essentially a closed system with the input here, and probably an output there, or something to that effect. And then inside this chamber, it's got a window just as a demonstration purpose, but inside this window you see the lamp, and it also have a quartz sleeve around it. So if the lamp is here, I think the quartz sleeve is like that. So anyway, you have those two layers, the lamp and the quartz sleeve, and then water's flowing by it. And the idea is to give essentially a minimum dose of UV light throughout the whole system for any water that's passing through, right? So you want to make sure that all the water in there, even the stuff that's furthest away from the light source, gets your minimum dose, so that the water has been treated according to the standards that have been put out. Okay, so taking a look at the light sources and the germicidal curve here, we have what's called the germicidal effectiveness. This is the curve that's essentially showing how DNA in general, could be ours, could be bacteria, could be viruses, is absorbing UV light. So we know that if we took light around 230, 240 range nanometers, it's actually not as effective as if we bring it up to our 254, and perhaps our 254 could even be better up at 265, given the light absorption. There are some other factors in terms of maybe quantum yields, stuff like that. But overall, you can see that there is some effectiveness difference. Our traditional or conventional mercury lamps do a pretty good job. These ones right here, this is the 254 emission I've been talking about. Does a pretty good job. It's very standardized. If we had fluorescent lights in here, which we don't, this is a new building, it's outdoor LEDs, but if we did, those actually are likely, the way they work, those fluorescent lamps, they emit this, but there's a coating on the outside of the lamp that is a fluorescent material that absorbs that light and then fluoresces in the visible spectrum. So if you were to scrape away that stuff, I think they might make the glass on those kind of such that the UV's not traveling through them too much, but you might be able to have some UVC exposure just from a normal fluorescent lamp if you scraped off the white coating. Would not suggest doing that. You'd probably break it and have a mercury vapor inhalation hazard on your hands. Fortunately, it's low pressure mercury, so it's actually not a whole lot of mercury, but still not a good thing to. If you do break a fluorescent bulb, get good ventilation, put it outside, let it waft away for a little while before you come back to it. We also have medium pressure mercury lamps. These have more of a polychromatic emission, including a pretty big UVB one that's kind of useless for germicidal, mostly useless. So there's a couple different things that have been out there. We'll talk a little bit about new LEDs that can operate here. We can maybe select different wavelengths a little more carefully. I think you probably heard a bit about that from Madhu's talk 2 weeks ago. So anyway, wanted to show you this. And another thing that is important to consider is water does absorb some of this just by itself. So there's some attenuation through water, and there's some attenuation by dissolved organics in water. So all of these things are ultimately affecting how many photons does the bacteria or the virus receive. Okay, so there's really two things at play here. Is what happens when the bacteria is hit by a photon of UV light, and how likely is it that it's going to be hit, or how many photons are coming through and making it all the way to the bacteria through the other stuff in the way. These the germicidal effectiveness, the way they, designed that curve or derived that curve was to check a few different organisms. So we have MS2. This is a bacteriophage, meaning it's a virus that infects bacteria. We use that in my lab all the time. And then C. parvum here, that's Cryptosporidium. And so these researchers were testing to see how much UV light of a specific wavelength was required to achieve some destruction of the organism, and they were plotting these data points, and so that's where you get this rough sketch of that germicidal effectiveness, that gray curve right here that we were talking about. So maybe this tails back upwards a bit, according to this one. And that might also depend on what type of organism you're dealing with, right? It looks like one that the virus is up here and the crypto is down here, so there's maybe some question about those wavelengths. You can do that with a few other ones, and really all of these are just taking a look at a given wavelength, what's that inactivation rate constant relative to, that's what this one's doing, relative to 254, the mercury emission that we use all the time. Can we get some improvement? So one here should be exactly the 254 right here. So that should be the baseline case right there. So it looks like if we do it, increase the wavelength to 265 or so, maybe we get some relative increase. So that's kind of neat. You may also get some benefit going lower. I've seen some technologies that may be able to do 222. Generally, it's going to be hard to have stuff that's emitting that you can also protect the lamp and have an emission through some material to get to water. That's not an easy thing generally, so that maybe that's not very feasible, but we'll see. Okay, so how does it work? So our UV damage, really what it's doing is it's causing what we call dimerization. So there's a few different types of molecule pairings in DNA that are vulnerable. One in specific is where we have two thymine groups next to each other. So if you think of a DNA strand as a zipper where you have the double strands here, and in order to replicate, you have to unzip, copy, paste, rezip, essentially. What's happening here is if you have these two thymine groups, UV light can excite them and cause them to react with each other and cross-link. So now you have these cross-linked thymine groups to form a dimer. So dimer simply means from Latin, so dimer is two, which is di, and mer is molecule. So a dimer is just two molecules bonded into one. So monomer, for example, that's a precursor to polymers, multiple molecules. It's one molecule. So if you polymerize monomers together, you have a polymer, plastic, right? So that's just a little bit of, it's the dimer there, monomer there. Just a little linguistics there for you. Okay, so what happens then if the UV light is causing these dimerizations is really you're no longer able to replicate as planned, and it's as if you took some super glue and put it between two pegs on a zipper, and then you try to zip it after it dries. That's not going to work out so well. You're going to have a bit of a problem. So that's kind of the way to conceptualize that. And you see here, so in normal DNA, it's being replicated over here, unzipped, and then if you have this dimerization between two thymine groups, then you're going to have an issue where it gets to this point and comes to a stop, can no longer proceed. So that's a way in which UV light may be able to sterilize an organism without killing it. Now, of course, this type of damage and other reactions are going to be occurring in an organism. So if you have a complex, a cryptosporidium cell, there may be other things that get damaged in the cell that cause it to stop functioning or cause it to die or whatever. But from the perspective of DNA damage, maybe its DNA is damaged, but it can still function as a cell for some amount of time. So long as it's not able to then repair those functions, we're okay. With UV light, I mentioned already that a few things about light attenuation. We don't want our, we have to make sure that the bacteria or the virus is receiving as much light as we think it is. So if we have suspended particles and they're causing some diffraction or reflection of light, that's going to be a huge hazard because bacteria may be behind them or even on the particle itself and then protected from the UV light. It could be that bacteria are existing within a particle itself. Maybe some particle formed and there's a bunch of bacteria inside that particle. You disinfect the water and then you drink the water, but those particles then dissolve in your stomach and then you have lots of bacteria in your stomach that you thought should have been killed. So particle removal is very important. Again, this is why we pretty much always do our disinfection step after all the filtration, sedimentation, all those things. Just like chlorination, which you don't want chlorine reacting with particles, reducing the effective chlorine. You don't want chlorine, you don't want bacteria protected against chlorine from, by being stuck with inside a particle. And it's just nice if you can remove particles, then you can remove any bacteria, viruses that are stuck to or within the particles. So makes sense, and here's just another reason why. So when we want to define how much light a a portion of water is receiving. The way we would quantify it, and the way we would quantify the reduction in light as it travels through water, would be really dealing with the Beer-Lambert law in terms of the light transmittance and attenuation. So you've probably done, in pretty much any chemistry course, chemistry lab, you probably used the Beer-Lambert law in some way or another, even if you didn't realize. So this is relating to, you have some initial light traveling, it passes through your sample, and if it's absorbing that light, then some of it's been reduced. So the most common way would just be to use a UV Vis Spectrophotometer. This is where you take a little UV, or a little transparent cuvette. Probably been trained to carefully clean all the edges of the cuvette, because that would certainly change the amount of light passing through it if you had fingerprint smudges and stuff. And then you put in your sample and you put it in this system, and then it spits out some sort of number. But what that really is spitting out is the difference of light between these two values. So that number readout is giving you, if the incident light was, let's say, 1, and the transmitted light then was like 0.2, then the absorbance value is relating those two based on this log equation here. So let's take a look at that. So the equation is the log of the measured intensity divided by the initial intensity. So essentially, the I naught here is the intensity if you never put a sample there. If you just have pure water, you blank it, that's your initial. Then you add your sample, you have something in it, and then you're reducing that. So presumably this is going to be a fraction here. And you say that's going to be equal to this negative, this thing, so that's going to be the molar absorptivity. I think I've got another slide describing this, but I'll go ahead and write it out. So this molar absorptivity is describing how many photons of this particular light does this particular molecule absorb per mole. So it's on a molar basis. It's really per moles per liter, right? So it's concentration basis. So this would be for a given wavelength times the concentration of whatever chemical you've got. And that's where the molar basis comes in. And this is so this should be say at wavelength lambda. And C of x, or Cx, is molar concentration of x. Okay, so just as a quick example, you can take a look at this graph here where we see that there's the US, actually I'm not sure which one that is. USR, that's some sort of river, not sure which river, natural organic matter, and then we have here SR, NOM's the Suwannee River, natural organic matter. So if we take natural organic matter from two different rivers, and we take a look at the profiles of their absorbance versus wavelength, so basically doing this for these molecules over a scan of wavelengths, what we see is there's kind of a similar trend, but a little bit of a difference there. So given the same amount of the organic matter, one type absorbs more light than the other. That means that one of these will require more UV light for our disinfection because it's absorbing the light and preventing that light from passing through and giving us the dose that we wanted. So that's to say that we actually have to watch for this and adapt our systems accordingly. If there's a big storm and it kicks up a lot of organic matter into our influent to our treatment plant, then we likely have to ramp up some of our disinfection right? And we have to be watching for that. There's even a few metrics like specific UV absorbance, seeing, okay, at our 254 nanometer mark, how much light is being absorbed by the organic matter. So we have metrics like that. Okay, so there's a few things that then impact the light intensity, how much light gets through our water. Now, how do we equate then, given some amount of light, how do we equate that to a disinfection? And it turns out this is actually rather straightforward, so much so that I kind of don't even need to teach it to you in a way. I mean, there's some jargon here, there's some terms, but effectively, unless I'm like giving you a radiometer and telling you to make some measurements and account for them, really it's just like the disinfection with a chemical. It's just, instead of a contact time, it's a dose in terms of intensity times time. So instead of like what concentration of chemical we're dealing with, it's like how much intensity of light are they receiving over time. So it's either a concentration of chemical over time or it's light over time, right? It's pretty much the same exact principle. So the Chick-Watson kinetics, they don't apply exactly, but it's analogous, okay? So let's take a look at this rate. If we have the rate of some organism being destroyed by some wavelength, subscript lambda there, is equal to negative n to the 1, that's our first order, that's the number of, that's our dn, right? So dn dt is equal to negative n to the 1 times this guy times our intensity. So what is this guy? This is the coefficient of specific lethality for wavelength of light lambda. So that would be, this would look a lot like, if this was our chemical system, it would be like saying minus n to the 1 times k times c. And that was c to the n, right? That was our Chick-Watson model for chemical disinfectant. So the analogy here is we have a coefficient of specific lethality, just like we did for the chemical system, and we have some intensity, a lot like we have some concentration of the disinfectant. Okay, presumably these two are constant, and so just like in our chemical system, we could say, we could use one parameter to accompany both of those, and in some problems that's probably going to be the case. So based on that, the analogous system there, we can expect that the units for, I don't even know really what this guy's called, I don't know. The units for this should be in per time, right? So then that would give us, if n is giving us a number concentration, and we need number of concentration per time to satisfy dn dt, then these two together should be 1 over time. And if we take a look at intensity is going to be some number of photons or some energy of photons per area. So that means this guy is probably going to be, as we see, area per energy. So intensity is often measured, as I just mentioned, in watts per square meter, or maybe milliwatts per centimeter squared, or something like that. So that's a energy received by some surface, okay? So if we have energy received by some surface there, and then this guy has some surface per energy, but that's not just energy, that's energy over time. So that ends up giving us, energy times time. So that ends up giving us, let's go ahead and write that out. So that's meters squared per joule times watts per meters squared. Meters squared cancel, obviously. And 1 watt is a joule per second. Is that right? Good. So that's going to give us, we could rewrite the watts here as joule per second. So that leaves us with 1 over seconds. Okay, so that works out as it has to. So that's good. So we can then just say that these two together, we can describe that as germicidal intensity. And in fact, that's really what was going on when we were taking a look at these graphs, specifically this one, or this germicidal effectiveness. They were taking, given a couple different organisms here, they were taking them and exposing them to light and figuring out, okay, given some intensity, how much of a kill was happening. So our dosage then is really just this germicidal intensity times time. Just like our dosing for like a chemical system would be CT, that CT concept that we talked about, meaning that given some concentration of an organism, it's just how much time do you need. You can either change the time or you can change the concentration to get your desired destruction of microbes. I think we took a look at some graphs of that, which I'm not sure if I had a slide. So we may do some either homework or some other way of, I might come revisit this a little bit and show that CT concept graphically. But essentially, you could get 99% disinfection with a low dose, high amount of time, or high dose, low amount of time. There's like a linear relation there. Same thing applies to UV dosage. Okay, so just a small elaboration on UV dosage, and then we'll do a practice problem. So if our dosage is this, and here I'll call it average intensity, so intensity average times time, we can say that, so that D, that's our UV dose in millijoule per centimeter squared. That's the same thing as saying milliwatts per second, or time seconds per centimeter squared. Our average intensity, that's going to be just the average intensity that's the water is receiving at that given wavelength. Time is the exposure. We can also call this fluids. So dosage times time, or dosage is intensity times time, and that's essentially fluids. Okay, so with all of that, there's not actually a lot of calculations that are any different, right? So if we take a look at this, maybe we'll need to deal with the intensity and germicidal terms in problems, but that's really not any different than the Chick-Watson kinetics, where we're dealing with the concentration times that coefficient of specific lethality. And sometimes we'll have combinations where we're just given a term in per seconds or per minutes or something. I think our practice problem from the book does just that. So let's take a look here. So we have a company designing a solar-driven portable water disinfection system to be used by the military. The system is simply an inlet tube, a pump, a well-mixed chamber, and an outlet tube. Water is pumped continuously into the chamber, where it is irradiated with UV light before exiting through the outlet tube into a collection vessel. The disinfection rate constant for the UV light is 7.80 per second, and the bacterial count in the water must be reduced by 99.9%. Because the Army needs the unit to fit into a backpack, they require that the unit's chamber be no larger than 2 liters. How much water will the system be able to produce during 10 hours of sunlight? So we've got the solar-powered system, got a solar panel of some sort generating energy to provide UV light for this backpack unit. So go ahead and take a look, see if you can solve this problem, solving for that how much water. So identify what you're looking for, draw a schematic, and then start working on a mass balance to solve that. All right. So hopefully this was not too crazy of a problem. If there was some confusion, I expect it was really more so in the problem setup. So let's take a look. We would have this system, some sort of chamber, said it was well mixed. We had an inlet tube and an outlet tube, and presumably the light was shining into this chamber to provide that UV dosing, right? So given that we have an input and output, some sort of mixing happening, then this should be a CSTR, because it said water is being pumped continuously. And given that this is just a constant UV dose, presumably the sunlight is providing some threshold amount of energy, or maybe it's a battery system so that it can give the same amount of energy over the time, then we should reach a steady state for the system. Also kind of assuming we have the same water supply and it's not like changing in the amount of bacteria coming in or whatever. So the few assumptions, but pretty reasonable to assume steady state. So then we have a CSTR with a UV chamber. We have some reaction rate constant. And if we take a look at this, it's what it describes as the disinfection rate constant for the UV is 7.80 per second. Now, what I talked about earlier is that dose, or the intensity times that germicidal factor here. If you go back up to here, this combination here is effectively a per time unit if you combine the two. So it really didn't give us much information about the specific lethality or anything like that. It just gave us a per time unit for disinfection as a rate constant. So it didn't have to give us just that, but that's what it gave us. So we'll just go with that. I'm just going to call it K. And we could say that that is equal to this germicidal intensity times, the germicidal effectiveness times the intensity, but we don't have any information there. So we can just leave it as it is, right? It doesn't really matter. So that may be one source of confusion if you felt like you had to do something special there. But the trick was to take a look and notice that the units are simply in the form of a constant that you can use already. So no transformation necessary. All right, then the other piece of information that maybe we haven't solved problems like this before. We were given information about the N over N naught. That's the 99.9% required. So this is essentially the required treatment level that we need to attain. So if it's 99.9% is what the removal, then this is going to be 0.001 for the N over N naught as a fraction, because this is what's remaining, right? The N over N naught is what's remaining. And we could say that that's the same as saying 1 minus the removal as a fraction. So you ought to be, if you're not yet, you should be familiar with changing back and forth from like a 99.9% removal. That means there's 0.001 remaining. So if that is unclear, let me know. Can hash that out a little more, but at this point, I'm letting you know that I'm assuming you know how to deal with that. The volume for the chamber itself, that was 2.00 liters. The time for the device was going to operate was 10 hours, or you could say there's 60 minutes per hour, 60 seconds per minute. So that's 3,600 times 10, 36,000 seconds. we'll apply that in a little bit. And then really what we're looking for is how much water is produced over 10 hours. So how much water, that's going to be a volume produced. That's what we're looking for. And to get that, we need a flow rate, because that's essentially the flow rate for the system times the time, that 10 hours. So that's kind of the way we're solving this and what we need to do. Okay, does that problem setup make sense? Okay, so then we're off to the mass balance, and we say, since we know it's steady state, there's no accumulation, we'll have Q times N coming in minus Qn going out, minus our reaction term VKN, and we have basically everything except Q, so we need to solve for Q. Again, I like to start from this point. Technically, if you wanted to memorize the derivation for a first order decay reaction, you might have started from N over N naught equals 1 over 1 plus theta K. But if you notice, you're going to have to convert back from theta. You're going to have to invert this. I mean, and maybe that's a simpler way to do it. So you could maybe use that as a starting point if you remembered correctly, and all that would have worked in this case. I went ahead and started from here to solve for Q. So I said Q, we can separate from these other two terms, N naught minus N. So I just factored it out of these two, and I moved this part to the other side. Minus, I added it to the other side, so VKN. So basically I just added this to both sides and then swapped them back. And said Q, factored out the Q from these two terms, and it gives us that. So a bit of algebra, come back up here, and say Q then is going to be equal to VKN divided by N naught minus N. Now that's not super convenient because we don't have a specific value for N or N naught, but fortunately enough, we can simplify that. If we divide the top and the bottom by N, that's going to give us VK divided by N naught over N minus 1. Now again, you could have started from the other place, and then you had the N over N naught, you just have to flip it. Maybe that was a quicker, easier way, because then your theta is related to V and Q, then you solve for that. But this works too. It gets us in a term where we have a ratio of N to N naught. In this case, it's N naught over N, so we need to solve that real quick. So N naught over N equals 1 over 0.001, which is going to be equal to 1,000. So Q then is going to be that 2 liters times our K, 7.8 per second, divided by 999, because that's 1,000 minus 1. So Q, go ahead and grab our Excel sheet here. So Q then was 0.0156 liters per second. So that was almost our answer. Now we need to multiply that by 10 hours. Of course, that's in seconds, so we'll use the 36,000 seconds instead, and that will give us our volume produced. There's 562.2 liters. Okay, does that make sense? Any questions or issues online or in person? All right. I think what I'm going to do, I could get into some more UV stuff about regrowth, but I think what I'll do is log into Kahoot real quick, and also give you a tiny commentary on COVID, given that we're talking about disinfection. And I know not everybody wants to hear more about COVID. I think I have a pretty unique perspective, though, so hopefully that'll be interesting, if nothing else. Okay, and that's pretty much the end of the slides here. All right, so my opinion is we're kind of going about COVID the wrong way. It is a serious problem, but it's not a serious problem for everybody, right? It's a serious problem if we get a situation where our hospitals can't take care of everybody they need to. But assuming we can avoid that, then it's not a problem that everybody, in my opinion, has to be as affected by as they are. I think a pretty good analogy is actually chickenpox. So if you don't know, chickenpox is pretty dangerous if you get it when you're older. There's an excellent article, I will find it and link it for you. It was published sort of at the beginning of the pandemic, which is now an endemic disease, I believe. Talk about that more in a moment. But the article was suggesting that there was a Russian epidemic that became a pandemic in the 1890s with some sort of a respiratory virus. I think it was probably called a flu back then, which was likely a novel SARS virus, or a similar novel virus that acted as a cold, in terms because COVID is acting like a cold virus in the sense of the transmissibility, seasonality, those types of things is very much a cold virus, and there are other coronaviruses which are common colds. So the idea was that with no exposure to it prior, you're pretty vulnerable to a hyperreaction. And somebody with compromised immune systems, or with, elderly, or obesity is another big risk factor. A first-time exposure to something it obviously can be lethal, but it seems like if you've had COVID before or had a vaccination, then you're much less at risk, right? So if you had chickenpox as a kid and then you get it as an adult, you're pretty much okay, right? You're either immune to it or it's not such a big deal. But what you don't want is to get it as an adult for the first time, because that's a much worse case. Obviously, there's some holes in that analogy. It's likely not a perfect one, but my thinking is that the best thing we could do is to provide exposure to the people that are not vulnerable. So kids, people who are healthy and have no underlying comorbidity factors or vulnerabilities, especially college-age students. Like even myself, I don't find myself to be at risk. I got vaccinated, had no problems with that. I don't know it's the right thing to require that for everything in the world, especially if you've already had exposure to it, especially if you are young and healthy and okay to get it. I don't think it's right to expect we're going to get rid of it altogether. And it looks like vaccinations can't do that in the first place. So there's maybe a few controversial opinions there. But I think that it is an important thing, but I think we can do a lot better about it than wearing my silly flimsy mask that's not probably doing a lot. Actually, I read through the mask mandate, the Louisiana mandate the other day, and apparently I think tomorrow they're going to make some new announcement, and who knows what LSU will do. But I did notice that They do make an exception for people speaking to audiences and to anybody that's potentially hearing impaired. So I should probably just stop wearing the mask when I teach. I don't know. Maybe next time I'll ask if you guys would like that. do your other teachers do that? Yes and no? Some? I mean, it's kind of... I like to see people's faces more than I like to see masks. So, I don't know. Maybe I'll start doing that. Maybe LSU will fuss at me. I don't know. Probably not. So anyway, hopefully that was a little bit different of a rant than you were expecting. So let's do a quick attendance. I'm going to try to do something more interesting here. I know I've been not really doing anything interesting attendance-wise, and I'm still behind on collecting these and sorting them out. If anything, that means that I'll have to be give more credit than I would have if I lost track of anything. So anyhow, let's give this. I guess maybe there's 3 people online that are not actually paying attention. Nope. 2 people. Okay. I'm going to go ahead and get started. So join in quick if you didn't. You guys have any fun Halloween plans? Yes and no? Studying. I'm going to try to get another homework up for you soon. Next topic is going to be water softening, which I haven't really... I will be developing new course material for that. Hopefully won't affect you much. It might be a little less polished than my other lectures, but should be interesting. It's an elaboration on equilibrium chemistry and kind of charge balance in light of that in solutions. So that's kind of the plan, and then yeah, I'll take a look at the syllabus, make sure we're on track for the exam, or give you any updates in that regard this week. Okay, so with that, that'll be it for today, and we'll see you guys next time.